Hello everybody. In this session, we discuss the basic concepts of experimental design and completely randomized design. The entire topic is divided into the following subdivisions. 1. Terminologies. 2. Principles of experimentation. 3. Completely randomized design. 4. Least square estimators of the parameters. 5. Statistical analysis. 6. ANOVA table. 7. Advantages and disadvantages of completely randomized design. 8. Example. 9. Conclusion. First section is terminologies. We discuss here some of the terms which are used in discussing designs of experiment. Experiment. What is an experiment? An experiment is a device to obtain answers to some scientific query. It is a process or study that results in the collection of data. The results of experiments are not known in advance. In comparative experiment, we compare the effects of two or more factors on some population characteristics. Example, comparison of different varieties of crops, different fertilizers in agricultural experiment, different medicines in a medical experiment, etc. Experimental design. Experimental design is a process of planning a study to meet the specified objectives. Planning an experiment properly is very important in order to ensure that the right type of data and a sufficient sample size and power are available to answer the research questions of interest as clearly and efficiently as possible. Experimental units. The smallest subdivision of the experimental material to which the treatments are applied and on which the variable under study is measured is called an experimental unit. Thus, in an agricultural field experiment, the plot of land on which a treatment is applied is an experimental unit. In a feeding experiment of animals, an animal is an experimental unit. Treatment. Various objects of comparison in a comparative experiment are called treatments. For example, in an agricultural experiment, different fertilizers or different varieties of crop are treatments. Blocks. Experimental units are collected together to form a relatively homogeneous group. This group is called a block. A block is also a replicate in designs of experiment. Experimental error. Even when same treatment is applied to different experimental units, the result will vary. A part of this variation is systematic and can be ascribed to different known sources. The other unexplained part of variation is called experimental error and includes all extraneous variations due to inherent variability in the experimental units, errors of measurements and lack of representativeness of the sample to the population of interest. Principles of experimentation. The experimental design involves the three basic principles. They are randomization, replication and local control. Randomization. The first principle of experimental design is randomization. It is a random process of assigning treatments to the experimental units. The random process implies that every possible allotment of treatments has the same probability. The purpose of randomization is to remove bias and other sources of extraneous variation which are not controllable. Hence, the treatments must be assigned at random to the experimental units. Replication. What is replication? The second principle of an experimental design is replication, which is a repetition of the basic experiment. In other words, it is a complete run of all the treatments to be tested in the experiment. In all experiments, some variation is introduced because of the fact that the experimental units such as individuals or plot of land in agricultural experiments cannot be physically identical. This type of variation can be removed by using a number of trials. We perform therefore the experiment more than once. That is, we repeat the basic experiment. An individual repetition is called a replicate. The number, the shape and the size of the replicates depends upon the nature of the experimental material. Local control. The term local control referring to the amount of balancing, blocking and grouping of the experimental units into number of homogeneous subplots. Balancing means that the treatment should be assigned to the experimental units in such a way that the result is a balanced arrangement of the treatments. Blocking means that like experimental units should be collected together to form a relatively homogeneous group. The main purpose of the principle of local control is to increase the efficiency of an experimental design by decreasing the experimental error. It can be observed that all extraneous sources of variation are not removed by randomization and replication. In other words, we need to choose a design in such a manner that all extraneous sources of variation are brought under control. For this purpose, local control is implemented. Now, we will discuss a simple basic design, completely randomized design. In short, it is also called as CRD. This is the simplest type of design based on principles of randomization and replication. A total of n experimental units are available for use in the experiment. These experimental units are as homogeneous as possible. That is, no source of variation can be recognized among them under any grouping or arrangement. Suppose that we have P treatments whose effect on the response has to be investigated. The experimental plan is to subdivide the n plots randomly into P parts such that jth part consists of nj plots. Sum of all nj is equal to capital N, the total number of experimental units available. Now, the first treatment is allocated to the first set of n1 plots, the second treatment to the second set of n2 plots, etc. The arrangement of n plots into groups n1, n2, etc. np plots is done in a completely random manner. Hence, the design is called completely randomized design. The completely randomized design utilizes the principles of randomization and replication in the following way. Randomization. Here, first ni experimental units are selected at random and ith treatment is allocated to these experimental units. So, the experimental units are selected at random. Replication. Since each treatment appears ni times, that means the ith treatment is repeated ni times. So, the replication is also involved. The data can be tabulated as follows. Suppose we have P treatments, name them as 1, 2, 3, etc. P and entered in the first column. The observations y11, y12, etc. y1 n1 receiving the first treatment The second treatment has the values y21, y22 etc., y2n2 so on. The observations yp1, yp2 etc., ypnp receives the pth treatment. The last two columns are the totals of the different treatments, that means y1 dot is the total of the treatment 1, y2 dot is the total of treatment 2 etc., yp dot is the total of treatment p, y bar 1 dot is the average of treatment 1, y bar 2 dot the average of treatment 2 etc., y bar p dot is the average of treatment p. Here the statistical analysis is similar to that of one-way classified data. Represent Yij as the jth observation taken from the ith treatment. There will be in general ni observations under the ith treatment. The model for this data is Yij is equal to mu plus alpha I plus epsilon ij, I taking the values 1 to p and j taking the values 1 to ni, where mu is the general effect, alpha I is the ith treatment effect and epsilon ij is the error term. The same model used under one-way classification. Least square estimators of the parameters. The parameters in this design are mu, alpha 1, alpha 2 etc., alpha p. The parameters mu and alpha i's are estimated by the methods of least squares, that is by minimizing the error summa square. So, what is error summa square? The error summa square is summation, double summation. First summation is for I is equal to 1 to p, the second summation is for j is equal to 1 to ni epsilon ij square. So, the error is epsilon ij is equal to yij minus mu minus alpha I, hence error summa square from all the observations together is double summation epsilon ij square, that is given by double summation. The first summation is for I and the second summation is for j, yij minus mu minus alpha I whole square. Now, choose the values of mu and alpha I, say mu hat and alpha I hat, that minimizes the error summa square denoted as L, which is obtained by solving p plus 1 simultaneous equations dou L by dou mu is equal to 0 and dou L by dou alpha I is equal to 0, I is equal to 1 to p. Dou L by dou mu explains or represents the partial differentiation of the error summa square equation L. Similarly, dou L by dou alpha I explains the partial differentiation of the error summa square L with respect to alpha I. Differentiating with respect to mu and alpha I and equating to 0, we obtain the p plus 1 equations called the normal equations as follows. Differentiating dou L by dou mu is equal to 0, we get n mu plus summation I is equal to 1 to p ni alpha I is equal to double summation I is equal to 1 to p, j is equal to 1 to ni y I j. And differentiating L with respect to alpha I and equating to 0 and simplifying, we get the equation ni mu plus ni alpha I is equal to summation j is equal to 1 to ni y I j. There are such p equations. These normal equations are not linearly independent, as the first equation is equal to the sum of rest p equations. Hence, no unique solution exists for mu and alpha I is equal to 1 to p. Since we have defined the treatment effects as the deviation from overall mean, we add a independent constraint summation I is equal to 1 to p ni alpha I is equal to 0 and solve the simultaneous normal equations. Solving these p plus 1 normal equations, we get the solutions as mu hat is equal to y bar dot dot and alpha I hat is equal to yi dot bar minus y bar dot dot. I is equal to 1 to p. The fitted model, after substituting the estimates mu hat and alpha I hat in the linear model, we get Yij is equal to mu hat plus alpha I hat plus epsilon ij. Now, you substitute the value of mu hat and alpha I hat in the above equation, we get Yij is equal to y bar dot dot plus y bar I dot minus y bar dot dot plus Yij minus y bar I dot, or I will take y bar dot dot to the left hand side. So, we get the equation as Yij minus y bar dot dot is equal to y bar I dot minus y bar dot dot plus Yij minus y bar I dot. The error term is chosen that both sides are balanced. Squaring both sides and summing over all the observations, we write the above equation as double summation I is equal to 1 to p, j is equal to 1 to ni, Yij minus y bar dot dot whole square as summation I is equal to 1 to p ni into y bar I dot minus y bar dot dot whole square plus double summation I is equal to 1 to p, j is equal to 1 to ni, Yij minus y bar I dot whole square, and the cross product vanishes, or we can write SST is equal to SSTR plus SSE, where we define SST is equal to summation I is equal to 1 to p, j is equal to 1 to ni, Yij minus y bar dot dot whole square, or that also can be written as double summation, one is for I, the second summation is for j, Yij square minus y dot dot square by n, which is a simplified formula for computation. Similarly, SSTR is summation I is equal to 1 to p ni into y bar I dot minus y bar dot dot whole square, that can be simplified as summation I is equal to 1 to p y I dot square by ni minus y dot dot square by n. And the error summa square is double summation, one is for I, the second summation is for j, Yij minus y bar I dot whole square, and which is computed as SSE is equal to SST minus SSTR. We can observe that even in one way analysis of variance technique, the same terms we have obtained, that is sum of squares is divided into two square terms SSTR and SSE. So, observe that the total corrected sum of squares can be partitioned into a sum of squares of the differences between the treatment averages and the grand average SSTR plus the sum of squares of the differences of the observations within treatment averages, that is SAC, or the error sum of square. So, the statistical analysis is similar to the analysis of one way ANOVA. So, here we investigate a formal test of the hypothesis H naught, alpha 1 is equal to alpha 2 etc. is equal to alpha p is equal to 0 against the alternative H 1 at least one alpha I not is equal to alpha j for every I and j. Here we have assumed that the errors epsilon ij are normally and independently distributed with mean 0 and variance sigma square. Hence, the observations Yij's are normally and independently distributed with mean mu plus alpha I and variance sigma square. Thus, SST is a sum of squares in normally distributed random variables, hence can be shown that SST by sigma square is distributed as chi square with n minus 1 degrees of freedom. Further, we can show that SSE by sigma square is chi square with n minus p degrees of freedom, and that SSTR by sigma square is chi square with p minus 1 degrees of freedom if the null hypothesis is true, that is H naught alpha I is equal to 0 is true. It also implies that SSTR by sigma square and SSE by sigma square are independently distributed chi-square and the variables. Therefore, if the null hypothesis is true, the ratio f alpha is equal to SSTR by its degrees of freedom whole divided by SSE by its degrees of freedom, that is mean SSTR divided by mean SSE, is distributed as F distribution with p minus 1 and n minus p degrees of freedom. Equation 1 is the test statistic for testing H naught. There is no differences in the treatment means. The whole procedure we will summarize in the following in our table, analysis of variance table. As we have discussed already, analysis of variance table consists of the following columns. The first column gives a source of variations, the second column gives degrees of freedom, the third column gives a sum of squares, the fourth column gives mean sum of squares, and the last column gives f value. In one way another, or in completely randomized design, only treatments are affecting the response, hence the total sum of square is split into treatment sum of squares and error sum of squares. So, the total variations are, the different variations are the total, the treatment and the error. Write down the corresponding degrees of freedom in the second column. For treatment it is p minus 1, for error it is n minus p, and for total it is n minus 1. For error actually it is calculated as the degrees of freedom of total n minus 1 minus the degrees of freedom for treatment p minus 1, which gives n minus p. The third column gives different sum of squares. So, first enter treatment sum of square, next enter total sum of square, next enter error sum of square, which is obtained as total sum of square minus treatment sum of square. In the fourth column, obtain the mean sum of squares, and the last column obtain the ratio, that is treatment mean sum of square divided by mean error sum of square. We reject H naught and conclude that there are differences in treatment means if f naught is greater than f alpha p minus 1 n minus p, where f naught is computed from equation 1 and f alpha p minus 1 n minus p is the table value referring to f table at alpha level of significance corresponding to p minus 1 and n minus p degrees of freedom. Advantages and disadvantages of CRD. Advantages. CRD design is very simple to implement. In this design, any number of treatments can be used with unequal replications and does not make the statistical hypothesis complicated. Third advantage, the statistical analysis is simple. Even if some or all the observations for any treatment is missing, the statistical analysis of the data does not become complicated. The design provides maximum number of degrees of freedom for the estimation of error variance. For small experiments, the precision increases with increasing number of error degrees of freedom. Disadvantages. In most circumstances, the experimental units are not homogeneous, particularly when a large number of units are involved. The CRD fails to take account of the variation among the experimental units as it does not use the principle of local control. This will increase the value of error variance under CRD. CRD is appropriate only if all the plots are homogeneous. In reality, this will never happen in field experiments. Thus, CRD is not recommended for field experiments. Let us discuss the complete analysis using an example. Consider the following example. A set of data involving 4 tropical feedstuffs named A, B, C and D tested on 22 chicks is given below. All the 22 chicks were treated alike in all respect except the feeding treatment. That means, all the chicks are treated as homogeneous. Let us analyze this data. Data is given: weight gain in chicks fed on different feeding materials composed of tropical feed stuff. So, the first treatment or first kind of food stuff is given to 6 chicks and the values are 55, 49, 42, 20, 62, 73. Similarly, the second row gives the values of or weight gain of chicks fed with the food stuff B. The third row values gives the weight gain of chicks when they are given food stuff C, and the last row gives the weight gain of chicks when they are given food stuff D. How to analyze the data? Here we observe that there are 4 treatments A, B, C and D, and we have to compare these 4 treatments on the response variable, that means in weight gain. Only the treatments foodstuffs affecting the weight gain other than general effect. Hence, we can assume one way ANOVA model. The model we assume here is Yij is equal to mu plus alpha I plus epsilon I j, where I is taking the values is equal to 1, 2, 3 and 4, j is taking the value is equal to 1 to ni. That means, we have n1 is equal to 6, n2 is equal to 5, n3 is equal to 6 and n4 is equal to 5. Mu is the general effect, alpha I is the ith treatment effect and epsilon ij is the error term. Here we are interested in testing the hypothesis H naught alpha 1 is equal to alpha 2 equal to alpha 3 is equal to alpha 4, that is equal to 0 against the alternative H1 at least one alpha I naught is equal to alpha j for all I and j, where I and j takes values 1, 2, 3, 4. Step 1. Calculate the correction factor, that is y dot dot square by n, which is given by summing all the values, summing all the 22 values, square it, divide by the total number of observations 22. So, it gives the value 160.0483. Step 2. Calculation of total summa square. The total summa square is given by double summation Yij square minus y dot dot square by n. So, Yij's are calculated as each individual observation square, that is 55 square plus 49 square etc. 154 square minus the correction factor, and on simplification it is equal to 37,793.318. Step 3. Calculation of treatment summa squares. First, you compute the totals of each treatments, that is first treatment total is 301, second treatment total is 355, third treatment total is 509 and the fourth treatment total is 714. So, using the formula summation I is equal to 1 to p y I dot square by ni minus the correction factor is given by 301 square by 6 plus 355 square by 5 plus 509 square by 6 plus 71 square by 5 minus the correction factor, and it simplifies to 25,583.152. Step 4. Calculation of error summa square. So, error summa square is given by total summa square minus treatment summa square. So, after simplification that gives 12,210.167. We will now summarize everything using ANOVA table. So, ANOVA table consists of the following columns. The first column is source of variation, next is degree of freedom, next is sum of squares, next is mean summa square and F ratio. Here only 3 sources: total, error and treatments. There are 4 treatments. So, degrees of freedom of treatment summa square is 3, degrees of freedom of total is 21 because there are 22 observations. 21 minus 3 is equal to 18 is the degree of freedom for error. Substitute the values of summa squares of total, of treatment, and for error it is obtained as TSS minus SSTR. Divide these summa squares by the respective degrees of freedom. So, we will get mean summa squares. Compute the F ratio, that is the ratio of mean treatment summa square by mean error summa square, which gives the value 12.571. Referring to F table, the table value at 5% level for the degrees of freedom 3 and 18 is 3.16. Observe that F calculated is 12.571, which is greater than the table value, hence we reject alpha. Hence we conclude that all the treatment means are not equal. Whenever H naught is rejected, we can go for multiple comparison test if needed, which gives the test which pair of treatments are significantly different. So, for that we proceed as follows. Compute each pair y bar I dot minus y bar j dot, and also compute T alpha n minus p root of mean error summa square into 1 by ni plus 1 by nj. The table value for T at 5% level with 18 degrees of freedom is 2.101. The absolute differences of y bar I dot minus y bar j dot is given in the following table for different combinations. A and A no value, A and B 25.73, A and C 39.23, A and D it is 97.28, etc. Compute all the absolute differences y bar I dot minus y bar j dot. Calculate the critical differences using the formula as said above, T into root of mean error summa square into 1 by ni plus 1 by nj. The values are given in the following table. Observe that the mean difference is significant at 5% level for the pairs A and C, A and D, B and D and C and D. So, which says that these pairs are significantly different. That means, the treatments A and C are significantly different, the treatments A and D are significantly different, the treatments B and D are significantly different, and the treatments C and D are significantly different. Conclusion. In this session, we have defined some terminologies which are used in design and analysis of experimentation. We have discussed the principle of experimental design. We have introduced completely randomized design and discussed its analysis. We have derived the least square estimators of the parameters of the design. We have summarized the complete analysis of CRD using ANOVA table. We also discussed the advantages and disadvantages of CRD. We have discussed the entire analysis of CRD using an example. Thank you.